I welcome once again and you are watching the series of interview questions for Bhabha Atomic Research Center, and the very reason that we are coming out with the dedicated series on interviews related to BARC is that the interview of BARC is supposed to be different from rest of the interviews. They are long interviews and they check your in-depth knowledge about particular subject, and not only knowledge they check your divergent thinking and creativity also. So they will tend to ask you something which require a lot of thinking, and you should think and accordingly you should answer. So that is the approach you have to follow in BARC interview. Normally the interview is 45 minutes to 1.5 hours, and they ask you to tell your 5 favorite subjects. Some of them should be your core branch subjects, and then they ask you to go on the board something like this, and then they ask you to answer questions there, and then they keep on asking you more questions. So they start from very basic and then they keep on increasing the depth. And if you ask me honestly, they are not interested in the answers, they are interested in the approach. So what approach you are taking and how you are proceeding forward. So whatever you explain, keep telling that this is, I think, how it is going to be. And if they find you that you are approaching the answer and you are deviating, they may give you clue, they may give you hint, and then they make you reach the right spot. So that particular approach is required, and the time they spend, a lot of time they spend on each candidate, because they want to identify the right people with scientific temperament and scientific bent of mind. So that kind of approach which is required in R&D organization, research and development organization, research institute. So that is something which they are checking, and for that they go for in-depth analysis of a student. So this is how we are to proceed forward in BARC interview. So today's lecture is about strength of material. One question on strength of material, that is what I am going to discuss today. So the strength of material is one of the important subjects, as you know, for mechanical and civil students. And then the first question which was asked was, tell about various moduli of materials. So we know there are different modulus. We know that there is a modulus of elasticity. This is called Young's modulus of elasticity, Young's modulus of elasticity. So that is number 1, and then second is modulus of rigidity. Modulus of rigidity is another, and then there is a bulk modulus, and then there is a Poisson's ratio. So these are some of the moduli which you know, and out of these 4, if any 2 we know, then we can calculate others also, because there is a relation between these moduli. And if we know, like E is equal to 2g into 1 plus mu, E is equal to 2g into 1 plus mu. So suppose I know mu, suppose I know E, I can calculate g also, 3k into 1 minus 2 mu. So this is, as you know, these are the relation between these 4 moduli. So E, G, K, mu, these are the relations. Now this Young's modulus of elasticity can be calculated as the slope of stress strain diagram. So if a normal stress, normal strain diagram, if I give you, the slope of that gives you Young's modulus of elasticity. Similarly, the slope of shear stress, shear strain diagram, if I give you shear stress, shear strain diagram, the slope of that gives you modulus of rigidity. Bulk modulus defines the compressibility. This actually is the term which is related to compressibility, and Poisson's ratio is the ratio of negative of lateral strain over longitudinal strain. So that is something like this. So anyway, first question was modulus of material, and in which kind of loading do you calculate this modulus? That was the first question. So the student must have answered in this way. Then he said, okay, can you draw normal stress strain diagram and shear stress strain diagram. Let me tell you, normally you draw the normal stress strain diagram only. This is a normal stress strain diagram, and normally you go for the derivation of normal stress strain diagram, and tangent theta is equal to Young's modulus of elasticity. This is the normal stress strain diagram, and how do you draw the normal stress strain diagram? There is a machine called universal testing machine, UTM, in which you take the specimen, and specimen has a gauge length L0 and the area is A0, and then the pulling load is applied. That pulling load eventually gives you the stress, and that stress, induced stress, pulling stress, and then proportionally the strain, and you can draw this particular graph. This is the universal testing machine. Now the question was, can you draw the shear stress, shear strain diagram also? Yes, so shear stress, shear strain diagram, you know what is shear stress, you know what is shear strain. So if I give you a body, and that body is subjected to shear force, let us say F, then that body is going to undergo shear strain. So that shear strain phi, and this cross section area, if I give you this cross section area, then shear stress is nothing but shear force per unit area of cross section. So you know these particular things already. Now shear stress, shear strain diagram for the steel typically is like this. This is the shear stress, shear strain diagram. Now again, this is experimentally obtained. So what is missing is, like if you compare these two, so what is missing is, what is the difference between the two is this particular part. This is called strain hardening region. This is called strain hardening region, or this particular strain hardening region or work hardening, strain hardening, or this is also called work hardening region. In this, what happens is the value of strength increases from yield strength to ultimate strength, and this particular strain hardening is observed in metal forming processes where the material is subjected to some kind of loading, and in the plastic deformation leads to the strength enhancement in the strength of the material. So increase in the strength of the material because of metal working or metal forming, something like rolling operation. In the rolling operation, that is how it increases. So because of that, the strength increases. So that particular part, which is strain hardening, work hardening region, is something which is missing here. No doubt you will get in this particular thing the yield strength also somewhere, and yield strength basically and ultimate strength, those kind of things you will get, though it is a shear stress strain diagram, but yielding value and your ultimate values of the shear strength. So up to the elastic limit and ultimate shear strength, these values can be obtained. So but this is the main difference. So work hardening region is not observed. So shear stress strain diagram, shear and normal stress strain diagram. And what is the slope of this diagram giving you? Slope of this diagram is giving you modulus of rigidity. Do we draw this graph also? Yes, normally this graph is also drawn, we do that. So he asks you, can you plot shear stress strain diagram, and the next question was how they are different. How are they different, and which material I have drawn it for? It is the mild steel only. As you know, this is for mild steel and this is also for mild steel. If you draw, then you are going to get this shear stress, shear strain diagram, and from here you calculate the value of shear strength only. At what value do you get shear strength here? We get lower yield point pe yield stress as yield strength, and similarly up to elastic limit we get the value of shear strength. Normally shear strength is half of the yield strength. That is how do we get these two values. Now define Poisson's ratio, and what do you think is the significance of that? Now let me first tell you what is the Poisson's ratio. Now if I apply the pulling load on this component, so what is going to happen is, let me use different color, it is going to get elongated in this way. It is going to get elongated in this way. So what is we are observing is delta x is the length which increases and delta y is the length which decrease. So what is the strain produced along x axis? So if you see, the strain produced along x axis is delta x over x. What is x? X is the original length in x direction, and maybe we taken the total length, and this is the original y. So what is the strain produced in y direction? Strain produced in the y direction is delta y over y, and as you know, why I have taken negative is because the length in y direction has decreased, so I have taken it negative. Now what is Poisson's ratio is, now this is a longitudinal strain, this is why it is called longitudinal strain? Because it is in the same direction in which I am applying the load. In which direction you apply the load? I am applying the load F in the x direction. So for me, sigma x is the longitudinal stress and epsilon x is the longitudinal strain. This particular thing is called lateral strain. This is called lateral strain. And what is Poisson's ratio is minus of lateral strain over longitudinal strain. Minus of lateral strain over longitudinal strain. Now this epsilon y itself is a negative as we have written it, so this particular term normally is positive. No doubt its value is varying from minus 1 to 0.5, theoretical value varies from minus 1 to 0.5. So there are some material like biological materials in which Poisson's ratio is negative. What is the meaning of that? Poisson's ratio negative means if I am increasing the length, width is also increasing. Volume constancy is not there. Maybe density does not remain same. So there are certain kind of biological matter in which Poisson's ratio can be negative. But practically speaking, it should be 0 to 0.5, and for majority of engineering materials, the value of Poisson's ratio is varying from 0.25 to 0.3. So for majority of engineering materials, the value of Poisson's ratio is 0.25 to 0.3. That is what we should know. And this is the negative. So why negative is put? Because Poisson's ratio has to be positive, and hence negative ratio is true. So what is the significance? Sir, Poisson's ratio is used to calculate the lateral strain. So if we know the longitudinal strain, then lateral strain can be calculated if we know the Poisson's ratio of the material. Now anyhow, if I explained it, then he gives you this particular diagram, stress strain diagram he gives you, and tells you that for A and B, tell me which material has more Poisson's ratio. Now let me give you example. Value of Poisson's ratio almost is 0 for material like rubber. This is the stress strain diagram for rubber. This is the stress strain diagram for rubber. The stress strain diagram for cork kind of material, which is very hard, is like this, very brittle, very hard. Now Poisson's ratio of this is almost 0 value, and Poisson's ratio of this rubber is 0.5, and Poisson's ratio of this is almost 0. So if the material is very, very hard, then its Poisson's ratio is almost 0. And if you see the elasticity, this cork has high modulus of Young's modulus of elasticity, and rubber has very less Young's modulus of elasticity. It is looking like from there, that diagram. So if you use this particular kind of concept, as I told you in BAR's interview, he is not interested in answers. He is interested in the approach which you people are using. So the moment you draw, sir, rubber I know stress strain diagram, and it is easy to basically elongate rubber. It is easy that I can deform it, and when I deform it, lateral strain produced is significant, and rubber has maximum Poisson's ratio 0.5. That means there is a significant lateral displacement with the longitudinal displacement. So lateral strain is also significant. Okay, done. So it has high, and this one is not having any lateral. Normally brittle materials do not neck. Necking is not produced in brittle materials, so they have very less lateral strain produced, and hence they have less value of Poisson's ratio. That means as I move from low elasticity to high elasticity, Poisson's ratio decrease. From that point of view, this should have high value of Poisson's ratio. So it looks like, sir, this is a brittle material. This looks like a ductile material, and for ductile material, sir, Young's modulus elasticity may be less. That means lateral strain produced, necking can be there, lateral strain can be produced there, and if the lateral strain is produced there, then this Poisson's ratio can be significant. So maybe A has less Poisson's ratio, but B has high Poisson's ratio. That is how we can compare the two. Now, which material has high value of E? The slope of A is more. So Young's modulus of elasticity of A is more than Young's modulus of elasticity of the B. E of this is more and E of A is more, but Poisson's ratio of B is more. Now then he says, next question he says that can you write some equation, some kind of relation between E and mu, and this is the relation between E and mu. Now tell me one thing, if mu is more, E is more or not, and if mu is less, E is less or not. So from this graph it looks like as the value of mu increases, E should also increase, right or not? As the value of mu increases, that means in case of B, the value of mu is more, hence modulus of elasticity of B should be more, but it is not there. It is not looking like that one, it is not looking like that. So why do you think it is the case? Why do you think it is happening? Why not Young's modulus? Why not the Young's modulus of elasticity of A is more than that of B, knowing well that mu for B is A is less than mu of basically A. So mu of B is more and mu of A is less, that is what we know, but E is reverse. Why it is so? Now again I told you in the previous similar videos, you are basically getting caught in a trap. Whenever you want to compare two parameters, do not assume third G as constant if you cannot assume that. You cannot assume wrong things, because if you assume wrong things, then the interpretation will also be wrong. So son, when I am comparing mu with E, when I am trying to make some kind of linkages, now it is looking like E and mu are giving reverse relation. It is giving that these are giving reverse relations. So when you are comparing E with mu, you cannot assume G to be constant, because whatever parameter will change E will change G also. Young's modulus of elasticity and modulus of rigidity will be changed. So when we want to compare the impact of E on mu, we need to see how that particular thing is changing G also. So G is also one of the parameter, and you cannot assume it to be constant. So that would have been the answer. So what was the question in BRC interview? Okay, I am giving you two materials, one having high Young's modulus, another is having less Young's modulus. Tell me which one will have more Poisson's ratio and less Poisson's ratio. You cannot take help of the formula. All you could have said is either you give me the value of G also for both, maybe then I can answer, or you provide me the value of the value of this rubber, this particular two materials, the Poisson's ratio. If I know these two materials, then from there I can get to know that if I can compare rubber and cork, then from there I get a trend how it goes. And let me tell you one more thing also. Value of E shows longitudinal deformation. Value of shear strain gives you an idea of lateral strain also. That gives you lateral strain, because in whenever you calculate, whenever you apply the shear force, then you are calculating the deformation in two different planes, A, B, C. Now let us say A goes to A dash and B goes to B dash. This is A dash, this is B dash. So understand, A goes to A dash, that is longitudinal deformation. A to C is the transverse length. So this is a transverse length and this is a longitudinal deformation. So in case of shear, one layer shearing over other, you talk about transverse and longitudinal both. That is how it basically is the relation. So yes, we need to see the impact of change on G also, E also, and then only we could have commented on this. So yes, the thinking was important. So which machine do you use to calculate Poisson's ratio? Any idea about that? If I ask you which machine is used to draw the stress strain diagram, any idea about which machine is used to draw the stress strain diagram? You have already given the answer. The machine which is used to draw stress strain diagram this is the original area, this is the original length. The machine which is used to draw stress strain diagram is actually called universal testing machine. Now, whenever you use the universal testing machine, then on using universal testing machine, delta x, delta y. So, if you know delta x, if you know delta y, then the Poisson's ratio can also be calculated, delta y over y, delta x over x, and this one will be with the negative sign. This is the Poisson's ratio. So, from the universal testing machine, I get all the values. I get the values of delta x, I get the value of delta y, I get the value of x, I get the value of y. So, Poisson's ratio can be calculated using the universal testing machine itself, and you could have shown, and that is the reason it is called a universal machine. Why it is called universal? Because this same machine can be used to calculate different properties. It can be used to calculate different properties. That is the reason it is called universal testing machine. Okay, now the similar question, as I told you in BARC interview, what he will do, he will be giving you in 1 hour, he will be giving you 2-3 questions and sufficient time for you to think. He will keep on asking you next questions, and he will keep on increasing the depth of the questions and keep on asking the different questions. So, what is the maximum normal stress induced? This is the pure torsion case. This is the pure torsion case. What happens is T over J over is equal to tau over R. Now, torsional shear stress is equal to T over J into R. Now, T is the applied torque, and this is eventually R maximum is diameter divided by 2. So, maximum radius is d by 2, and that maximum radius gives me the maximum torsional shear stress. So, what is the maximum torsional shear stress we are getting here is 16T over pi d cube. A shaft subjected to the pure torsion, if the shaft is subjected to pure torsion, this is the shear stress which I am going to get. Now, when the moment you start applying the Mohr circle, start drawing the Mohr circle for this, this is the Mohr circle, center of the Mohr circle, and the normal stress and the maximum shear stress values are same, and this itself is the normal stress. So, what is the normal stress? Maximum normal stress induced in this is 16T over pi d cube. Which plane? Now, let us name this plane. Let us name this is AB plane and this is AC plane, let us say. So, this particular plane where you get the maximum shear stress, this plane is AB plane. This is AB plane, the transverse plane at which you are applying the torque is AB plane, and at 45 degree the plane of normal stress, maximum normal stress, the plane of normal stress is at 90 degrees. So, this is, let us say, AD plane. So, this one becomes AD plane. This is AB plane, that is the plane at which you are getting the maximum shear stress, torsional shear stress, and this plane you are getting, and then similarly you are getting the maximum principal stress at a plane which is at 45 degree from plane of maximum shear, and this maximum shear stress induced is this. That is how you get it. Now, if suppose this is a brittle material, can you tell me at which plane this is going to fail? If this is a brittle material, tell me at which plane it is going to fail. So, brittle material fails at 45 degree or AD plane. So, brittle material, if you take a piece of chalk and if you give a twist to a chalk, you will find that that particular chalk will fail at 45 degree. This is how it fails. This is the answer you could have given.